Outfitting a multi-floor plant or sprawling logistics hub with augmented reality places the physical space's geometry at the center of the engineering challenge. Most localized scans produce isolated coordinate systems, creating disconnected map islands. A digital model tracked in one zone has no inherent relation to the adjacent zone. As users or robots cross these invisible boundaries, tracking drift accumulates. Network dips create tracking latency, breaking spatial alignment and rendering the digital overlay useless. To compensate, teams often find themselves locked into specific hardware ecosystems, relying on a specific tablet's LiDAR or a proprietary scanner fleet to maintain a baseline accuracy. Deploying spatial computing at scale requires removing that hardware dependency and connecting the map islands. It demands a tracking system that remains stable, regardless of network performance. The MultiSet visual positioning system functions as a decoupled, software-agnostic routing layer. This architecture illustrates a unified data pipeline. Diverse capture inputs funnel into a single processing engine, which then normalizes the data for distribution to various edge devices. This structural shift allows the system to maintain 6 degrees of freedom tracking across virtually any architectural footprint, moving the coordinate system away from the physical sensor and into the software. The burden of spatial awareness is handled by intelligent, scalable algorithms rather than the limitations of individual hardware sensors. The first layer of this architecture is Scan-Agnostic ingestion. The engine natively reads raw LiDAR, Leica E57 meshes, NavVis point clouds, and Matterport matter packs, allowing teams to leverage their existing reality capture data. This shows the vision fusion process. 3 distinct point cloud formats move into a central fusion node. Within this node, the engine enforces a strict 1 unit to 1 meter scale, neutralizes lighting variations, and filters sensor noise to output a single, standardized, compression-optimized map grid. Normalizing these disparate formats into a single pipeline allows developers to focus on the user experience, instead of engineering hours spent on data translation. The MapSet feature provides the computational solution to the map island problem across large-scale facilities. This diagram shows how MapSet stitches fragmented zone scans together. These zones snap into a single, continuous floor plan through shared coordinate transforms. For operations, this enables uninterrupted tracking and robotic SLAM handoffs that remain consistent across multiple floors and entire campuses. This spatial continuity also extends to individual assets through MultiSet. MultiSet tracks physical assets using standard textured 3D CAD or GLB meshes, replacing the need for physical QR codes or markers. True spatial intelligence requires persistent anchoring that scales from a 100,000 square foot facility down to the specific geometry of a single desktop object. The runtime engine is built to a strict performance baseline, sub-6 centimeter accuracy at ranges of 100 meters, all within a 52 millisecond latency budget. Querying these massive spatial datasets on mobile hardware usually creates a significant bottleneck for the CPU and device memory. MultiSet bypasses this compute constraint using a mechanism called hint position. Without a prior, a device searches every node across the entire megamap to calculate its location. Hint position uses a GPS or UWB prior to instantly collapse that massive search space down to a tight micro-search radius around a specific coordinate node. This localized search resolves lookalike scenes, like identical warehouse aisles, and increases localization speed by up to 40% while reducing CPU load. VPS speed is a direct result of narrowing mathematical search parameters before the visual query begins. Once the spatial data is structured, it is deployed through a unified binary SDK. One identical SDK powers Unity, native iOS and Android, MetaQuest, WebXR, and ROS2, without code branching. Zero install endpoints like WebXR and AppClips allow users to launch spatial experiences from a QR code in under 5 seconds. To meet enterprise security requirements, the backend can be hosted on a public cloud, a private VPC, or within a self-hosted Kubernetes fleet. For air-gapped or high-security sites, the system supports fully offline on-device localization. This shows the offline architecture. A cloud server packages map geometry into a .bytes bundle and caches it directly to the mobile hardware. After a one-time license authentication, the server connection is severed. The device performs continuous localization loops entirely offline with zero network latency. Decoupling localization from network requests makes spatial computing viable in remote industrial sites and high-security facilities. This backend architecture is managed within the Unity editor through a simple development workflow. This schematic shows the initialization process, highlighting the SDK manager component in the inspector, where API credentials are authenticated. Developers then assign a specific map code to lock the digital environment to the physical facility. Finally, all standard Unity AR content is nested directly under the map space game object to ensure persistent anchoring. The SDK abstracts the underlying mathematics of vision fusion into a predictable drag-and-drop developer experience. MultiSet shifts the burden of augmented reality localization away from specialized hardware and onto algorithm-driven fusion. This architecture allows a worker in a complex industrial environment to perform hands-free inspections with digital overlays locked perfectly onto machinery, even operating entirely offline. Persistent spatial intelligence is realized when digital content anchors to the real world, independently of the hardware or network that delivered it.